So this is a homework problem
Homework now.
from chapter 4, section 4,
Number
number 1.
one. Number one and BC.
Okay. So in problem number 1, we have the vector space R2, and we have two bases. So the basis F consists of the vectors 1, 3, and 2, 7. And the basis G consists of the vectors 2, 0, 1, 1. And first we want to prove that these are bases for R2. So each of them has the dimension of R2 is 2. So every set of 2 linearly independent vectors
Yeah.
is a basis for R2. So let's look at F, for example. Suppose that, let's just write this as x 1, 3 plus y 2, 7 is equal to the 0 vector. This is the same as x plus 2y, 3x plus 4, 7. So we want to know what are all possible solutions of the equations x plus 2y equals 0, 3x plus 7y plus 7y equals 0. And if you solve these two equations, the only solution is x equal y equals 0. So these two vectors are linearly independent. And similarly, if we look at the basis G, if we take a linear combination of 2, 0 and 1, 1, this vector is 2x plus y, y. If that equals 0, then you can see right away that y equals 0, and 2x plus y equals 0 means x equals 0. So again, these two vectors are linearly independent, and we know that F and G are bases for R2. So that's part A. In part B, we want to compute the change of basis matrices. So let me just make sure I use the same notation for P and Q that I might have used earlier. So I want to compute a matrix P,
P and Q.
which will be a 2 by 2 matrix P, such that each of the vectors Gj is this linear combination. I goes from just 1 to 2, Pij Fi, and the 2 by 2 matrix Q, such that each vector Fj is a sum I goes from 1 to 2, Qij G sub I. right? So all that means is the following, right? So G1 is the vector 2, 0. And I want to write that as a linear combination of the vectors 1, 3 and 2, 7. And this will be P1, 1, 1, 3, P2, 1, 2, 7. And G2, which is the vector 1, 1, is going to be P1, 2, 1, 3 plus P2, 2, 2, 7. I have to compute these numbers, the P's. These are the coordinates of the change of basis matrix. In any case, I know it's possible to solve these equations because 1, 3, and 2, 7 are a basis for R2. So every vector is a linear combination of them. Let's see. What is this vector? This vector is P1, 1 plus 2, P2, 1, 3, P1, 1 plus 7, P2, 1.
Yeah.
So to find P1 and P1, 1 and P2, 1, we have to solve these equations. P1, 1 plus 2, P2, 1
Equal
equals
to
2, and 3, P1, 1 plus 7, P2, 1 equals 0. So, for example, so any way you solve it is okay. If I take the first equation, so let's just solve this. So I'll just use Gaussian elimination to make it simple, make it sort of algorithmic. So if I subtract 3 times the first equation from the second, I get 0. 7 minus 6 is 1. And 0 minus 6 is minus 6. So P2, 1 is minus 6. And just plug in minus 6. So I get P1, 1 minus 12 is 2. So it looks like P1, 1 is going to be 14. Let me just check. 14 minus 12 is 2. No, something's not right. Oh, maybe it is. 42 minus 42 is 0. So that's P1, 1 and P2, 1. And to get the other two coordinates, let's see, what is this? This is P1, 2 plus 2, P2, 2, 3, P1, 2 plus 7, P2, 2. And again, this equals 1, 1. So we're solving two equations in two unknowns. The two equations are P1, 2 plus 2P2, 2 equals 1. 3P1, 2 plus 7P2, 2 equals 1. Again, P1, 2 plus 2P1 plus 2P2, 2 equal 1. Subtract 3 times the first equation from the second, I get P2,
negative 2
equals minus 2.
negative 2, yeah.
So you plug in minus 2 for this. This minus 4 is 5. So
5.
it looks like P1, 2 is equal to 5.
Yeah.
Right, let me just check. 5 minus 4 is 1. 15 minus 14 is 1.
Yes.
So my matrix P is going to be 14 minus 6, 5 minus 2. And what does this mean? So let's look at it so from these equations that I started with, G11 is equal to 14, 1, 3 is F1, and P21 minus 6, F2. And this is G1. And the vector G2
Professor,
is,
can you move the paper, please? Thank you.
G2 is P1, 2 which is 5 F1 minus 2 F2. So if you take a vector V and the coordinate, so suppose V is a vector x times G1 plus y times G2. So the coordinate vector for V with respect to the basis G is the vector xy. That's the definition of the coordinate vector. These are the coordinates of V expressed as a linear combination of the vectors in the basis G. But what are G1 and G2? I can write this as x times 14F1 minus 6F2 plus y times 5F1 minus 2F2. This is equal to 14x plus 5y times F1 plus minus 6x minus 2y F2. So here I've expressed the vector V now as a linear combination of the vectors in F1 and F2. So I have the coordinate vector of V with respect to G is xy, and the coordinate vector of V with respect to the basis F is 14x plus 5y minus 6x minus 2y. It's that vector. Now, if we remember, we had the matrix P, which is 14 minus 6, 5 minus 2. So P times the vector xy, that's 14, 5 minus 6 minus 2 xy, that's equal to 14x plus 5y minus 6x minus 2y. So in terms of these coordinate vectors, this says if I take the matrix B times the coordinate vector for V with respect to G, I get the coordinate vector for V with respect to F. So this is P is the change of basis matrix. If I have a vector and I have its coordinates with respect to the basis G, P times that vector gives me the coordinate vectors for V, but with respect to the second basis F. Right? And so that's how we calculate the matrix P. So this is the changing basis from G to F. And Q, will be the change of basis matrix going in the opposite direction. This will be a matrix such that Q applied to the vector V with respect to F gives me the coordinate vector for V, but with respect to G. And to get that, I simply write each vector F1 and F2 as linear combinations of the vectors in G. This will be Q11 G1 plus Q21 G2. This will be Q12 G2 plus Q22 G2. I compute these coefficients, the Q's, and Q is the matrix Q11, Q21, Q21, Q22. So if you look just at, I'm not going to compute Q unless you want me to, but if you look at part C,
let V equal,
So in part C, we have the vector V equal to 5/3.
over. Mhm.
And
Okay.
and we need to compute the coordinate vectors for V with respect to F and with respect to G. So since I computed the matrix P, if I know the coordinate vector of V with respect to G, I can then use the matrix P to get the coordinate vector for V with respect to F. So suppose I want to write this as some linear combination xg1 plus yg2.
Mhm.
So that's x times the vector 2, 0 plus y times the vector 1, 1, which is 2x plus y, y. And I need to find x and y such that this equals 5/3. So you look at this and you see right away y is equal to 3. And if y is equal to 3, x has to be equal to 1. So the coordinate vector for V with respect to the basis G is 1, 3. And the coordinate vector for V with respect to the basis F will be P times the coordinate vector V with respect to G. P we calculated 14 minus 6, 5 minus 2. The vector V, the coordinate vector for V with respect to G is
1,
1.
3.
So you get 14
Calculate.
plus 15 is 29.
Mhm.
And minus 6 is minus 12. So let's just
And
check
then-
to see if this is correct. Right.
Uh-huh.
All right, so this says V is supposed to be equal to 29 F1 minus 12 F2. That's 29 times F1 is 1, 3, minus 12 times F2, which is 2, 7. So this is 29 minus 24, which is 5. This is 57 minus, let's see, 7 times 12 is 84. Sorry, 3 times 29, yes, 87. 87 minus 84 is 3.
Three.
So that is equal to
it's-
V. So
you
this
check.
checks.
Mhm. Okay.
And then you do similar calculations to, compute Q, the matrix Q.
Mhm. Yeah, thank you. I have the question for 11th, but I'll ask you afternoon.
Well, I'm happy to do it now. There's no reason not to if you like.
So 11, I submitted the 10, but I still missing some 9 and 11. So I think 11. No, 11, let me finish. I still have a lot of, so let me
Okay,
do
that's fine.
first. Yeah, let me do first. So we have today afternoon and tomorrow afternoon and Wednesday morning. So I
Right.
have 3 days to ask.
Right. Okay.
Thank you.
So let me then start again lecture 14 proper. But all I wanted to do, or what I want to do, is just review lecture 12. So I want to talk about inner product spaces. So if you took vector calculus, you saw that there's something, so in vector calculus, in R2, there's the dot product of two vectors. If you have vectors, they're written horizontally, usually in vector calculus, but I write vectors vertically. So if you take x1, y1 dot x2, y2, this is the scalar x1, x2 plus y1, or actually I prefer to write it like this, x1, x2, and y1, y2. So the dot product is x1, y1 plus x2, y2. And in R3, if you have the dot product of three vectors, that is three-dimensional vectors, it's this number, it's this scalar. So in calculus, this is sometimes called the dot product, also called the scalar product. And this is a special case of the general definition, the general idea of what is an inner product in any vector space. So an inner product is an inner product in a vector space is I'll just write down the words and then I'll define them again, is a symmetric, positive definite, bilinear form, called F. So let's say F from V cross V into the scalars. Let's just say the scalars are the reals for today. So V cross V, so V is a vector space, and V cross V is another vector space whose vectors are like pairs of vectors v1, v2, where v1 is in V and v2 is also in V. So we're looking at pairs of vectors, and we can define addition and scalar multiplication coordinate-wise. You have the pair v2 and the pair w1, w2. You add them by just adding coordinates, v1 plus w1, v2 plus w2, and a scalar times v1, v2. You just multiply each coordinate by the scalar, cv1, cv2. Because V is a vector space over R, so all this makes perfect sense. So this is the definition of vector addition and scalar multiplication in V cross V, and you can check that all the properties of a vector space are satisfied. Now, a function from V cross V to the reals is bilinear if it has the following properties. First, if I take V1 plus V2, comma W, so V1, V2, W, these are all vectors in V. F of this is, it's as if W were constant. It's like this is a linear transformation of the first variable. F of V1, so this is F of V1W plus F of V2W. And similarly, F of C times V1 comma W is C F of V1 W. So it's like, again, it's as if you held W fixed as a function of the first variable. This is like a linear transformation of the first variable. And the similar properties hold for the second variable. F of V comma W1 plus W2 is F of VW1 plus F of VW2, and F of VC times W is C times F of VW. So a function from V cross V to R is called a bilinear form. Is a bilinear form. If you hold one variable fixed, it's a linear transformation in the other variable. And a bilinear form is symmetric if f of VW equals f of WV for all VW and V cross V. So it's like the variables can commute. That's what a symmetric bilinear form is. And a bilinear form is positive definite if f of V comma V, so if you apply the form to a pair of where the first and second coordinates are the same, this is strictly greater than 0 for all V different from 0. If V is 0, this is 0, but for any V different from 0, this has to be strictly positive. It doesn't mean that the form is always positive for all pairs of vectors, only for pairs of vectors where the first and the coordinates are the same non-zero vector. And one can check that the dot product in R2 and R3 is a positive definite symmetric bilinear form. And in general, in a vector space V, any vector space, an inner product is a positive definite symmetric bilinear form. So, and let's take, again, the basic example, which generalizes the dot product from vector calculus. In Rn, if V is the vector x1 to xn, and W is the vector y1 to yn, we define the inner product, and we usually define the inner product without using a letter like F, just V comma W. You multiply coordinates pairwise and add. And again, if you look at this, I mean, some things are clear right away. If V equals W, that means Xi equals Yi. Let me just write this down. So if Xi equals Yi for all I, then the inner product of V and W is x1 squared plus x2 squared. It's just the sum of the squares of the variables. And it's greater than 0 if at least one of these coordinates is non-zero. Positive or negative doesn't matter. So, sorry, f of V comma V. So it's greater than 0 if V is not the 0 vector. The 0 vector has all coordinates 0. If V is not the 0 vector, then at least one of these coordinates is non-zero, so its square is strictly greater than 0, and the sum is positive. So, and also if you look at W comma V, that would be y1 x1 plus y2 x2 up to yn xn, but multiplication of real numbers is commutative. X1 y1 equals y1 x1 and so forth. So the inner product of V and W is the inner product of W and V for all V and W and V cross V. There are many other examples of inner products. So here's a fundamental example from calculus. Suppose we take the vector space V to be C0, 1. So this is a set of all continuous functions f from the unit interval, the real numbers from 0, 1 to R. So this is a vector space, and for vectors f and g in V, which means these are continuous functions, to find the inner product of f and g, if a function is continuous, you can integrate it. If a function is, if you have two continuous functions, the product is continuous. So multiply f and g, f of t times g of t dt, integrated from 0 to 1. So this defines, this associates a real number to every pair of functions. And this is bilinear. For example, if you have f1 plus f2 comma g, this is the integral from 0 to 1, f1 plus f2 of t times g of t dt. This is the integral from 0 to 1 of f1 of t g of t plus f2 of t g of t dt. The integral of the sum is the sum of the integrals. f1 of t g of t dt plus f2 of t g of t dt. This first integral is the inner product of f1 and g, and the second integral is the inner product of f2 and g. So f1, f2 comma g is f1g plus f2g. And in exactly the same way, this is all stuff you learned in calculus. If you take f and multiply it by scalar c, and take the inner product with g, that's the integral from 0 to 1 of cf of t, g of t dt. You can take a constant outside the integral sign. This is c times the integral from 0 to 1, f of t, g of t dt. This is c times, and the integral is, that's the inner product. So cf comma g is cf comma g. So this is bilinear. And it's symmetric because fg, which is the integral of f of t, g of t dt, is the same as the integral of g of t, f of t dt, which is the inner product of g and f. And if you take the inner product of f with itself, that's the integral from 0 to 1, f of t times f of t, that's f of t squared dt. And this function is continuous. If f is 0, of course, the integral is 0. But if is non-zero, then this function is strictly positive on some interval, subinterval. This is greater than 0 if f of t is not the 0 function. So this is the symmetry, and this is the positive definiteness. So this is another example of an inner product on a vector space. So you should not think that the only inner product is the standard inner product on the line. No. It's nice to be able to extend to vector spaces some simple notions of elementary geometry. So we say that non-zero vectors VW are, and there's three words that are basically synonymous here, perpendicular to each other, perpendicular, or orthogonal, or normal, if the inner product of V and W is 0. So for example, in Rn, if we let E be the basis, the standard basis, E1 up to En, this is the standard basis. So E1 is the vector 1 and everything else is 0. E2 is the vector 0, 1 and everything else is 0. In general, E sub j is all zeros. There's a single 1 and then everything else is 0 again. And the 1 is in the jth coordinate. A very useful function in mathematics is something called the Kronecker delta. It's defined by delta I comma j is equal to 1 if I equals j and 0 if I is different from j. So another way of writing this standard basis vector ej is the first coordinate is delta 1j, second coordinate delta 2j, the jth coordinate is delta jj, the nth coordinate is delta nj, and you'll notice these coordinates are all different except when j is j. So this is 0, 1, and then all zeros. So you can say that the standard basis vector ej has coordinates delta ij. I goes from 1 down to n. But this Kronecker delta is very valuable notation. And if you take the inner product of ei and ej, what is that going to be? Well, let's see. If I is different from j, this is the inner product of two vectors. Here, there's a 1 in the ith coordinate. Here, there's a 1 in the jth coordinate. And I is different from j. So when you do these pairwise products, everything adds up to 0. But if you take ei comma ei, that's standard inner product. Now the two vectors have their 1 in exactly the same place. So when you add up the sums of the pairs of coordinates, you get zeros plus 1 plus 0, you get 1. So in fact, for the standard basis, the inner product of ei and ej is the Kronecker delta ij. 1 if I equals j, 0 otherwise. And so we say that a basis for a vector space V, let's say dimension of V is n, and my basis, let me call it B. B consists of the vectors W1 up to Wn. This basis is orthogonal if the inner product of delta Wi delta Wj is 0 for all I different from j. So that means in this basis, the vectors are all perpendicular to each other. So for example, in R3, this is E1, this is E2, and this is E3. These three vectors are mutually perpendicular. That's an orthogonal basis. And so it's important and useful to be able to say when two vectors are perpendicular to each other in a vector space, and in an inner product space, the definition of perpendicular or orthogonal is that the inner products are 0. We say that a unit vector, we think of a unit vector has length 1. But we need to have a notion of length in a vector space. So we define the length of a non-zero vector V by, and we usually write double bars around the V. That's the length of V. This is equal to So V is non-zero, so the inner product is positive, so we can take its square root. So the length of a non-zero vector V is defined like this. So for example, the length of the vector EJ is the square root of EJ comma EJ. This inner product of a standard basis vector with itself is 1, and the square root of 1 is 1. So EJ has length 1 for all j. And a unit vector is a vector of length 1. What is the length of a zero vector? We define the length of the zero vector to be 0. And an ortho normal basis for V is a basis of mutually orthogonal unit vectors. So for example, the standard basis E1, this is the standard basis in Rn, is orthonormal. So for example, in the vector, let's say 3, 4, call that V. If V is the vector 3, 4 in R2, then the length of V is the square root of the inner product of V with V. If V is 3, 4, the inner product of V with V is the inner product of, it's 3 times 3 plus 4 times 4. That's 9 plus 16 is 25. So this is the square root of 25, which is 5, which is completely consistent with what you do in elementary calculus and geometry. If V is different from 0, then the length of V is positive. Notice, you have an inner product, so the inner product of a vector with a non-zero vector with itself is strictly greater than 0, so the square root always makes sense. So if V is non-zero, then the length of V is positive, and if I take the vector 1 over the length of V times V, I call that U, this is a unit vector, because the inner product of U with U is the inner product of 1 over the length of V, comma 1 over the length of V. This is a scalar, so I can take it outside. So this is 1 over the length of V times the inner product of V with 1 over the length of V times V. Again, this is a scalar. I can take that outside. So I get 1 over the length of V times the length of V. That's 1 over the length of V squared, V comma V. But the square root of V comma V is the length of V. So V comma V is the length of V squared, and 1 over something times something, these cancel out, you get 1. So this is a unit vector. So for example, the vector 3, 4 has length 5, so 1/5 times the vector 3, 4, which is the vector 3/5, 4/5, is a unit vector. In particular, if B is an orthogonal basis for a vector space V, then, so these are linearly independent, so they're non-zero. So if I let u sub I be 1 over the length of w sub I times the vector wi is a unit vector. What's dividing any vector by its length gives a unit vector, and the sequence u1 up to un, it still is orthogonal, but now these vectors are unit vectors. So this is an orthonormal basis for V. There's actually a very important inequality called the Cauchy Schwarz, let's spell it correctly, inequality. It says that for any vectors v and w, the inner product of v and w, that's a real number, take its absolute value, this is always length less than or equal to the length of v times the length of w. Which is, so this is really very, very important. It says, for example, in Rn with the usual inner product, if v is x1 to xn and w is y1 to yn, then the length of v is the square root of summation x sub I squared. The length of w is the square root of summation y sub I squared. I goes from 1 to n. So the inner product of v and w in absolute value, which is the absolute value of summation x sub I, y sub I goes from 1 up to n, is less than or equal to summation x sub I squared, summation y sub I squared. Or if you square this, you get another form of this, which is you take the sum x1, y1, x2, y2, up to xn, yn squared, that's less than or equal to the sum of the squares of the x coordinates times the sum of the squares of the y coordinates. So this is actually one of the most important inequalities in mathematics, Cauchy-Schwarz inequality, which is a special case of this general Cauchy-Schwarz inequality in any inner product space. I'm not going to prove that now, but I just want to point out that if I take this inequality, again, v is non-zero, w is non-zero. So if I take the inner product of v with w and divide by the length of v times the length of w, this is between 0 and 1. Or if I take away the absolute value signs, this is between 0 and -1. And if you take two vectors v and w, they form a plane. In that plane, you can think of there's an angle between those two vectors, and the cosine of that angle is defined to be the inner product of v and w, defined by the length of v times the length of w. There's actually a way to define, one can define the trigonometric functions from scratch using this definition. But That's actually how you define the cosine between two angles in the plane. And if you look at this for a second, let's see, let me actually call this V and this W. Suppose I drop the perpendicular from V to W. Just think of this as high school geometry. You have two lines, draw this perpendicular. The length of this, that's the length of V. This is what? This is, this over this is the cosine. So this is the length of V times the cosine of theta. Cosine of theta is this over this. So this times the length, that's cosine of theta. This is the projection of V onto W. It's the length of V times the cosine of theta. See, what is that? That's the length of V well, actually, I want this to be a vector. So this is the length of this vector, and it's pointing in the direction of W. So it's this times a unit vector in the direction of W. That's W over the length of W. So what is cosine V? Cosine theta is VW over the length of V, length of W, times W over the length of W. These cancel. This is the inner product of V and W over the length of W squared times W. So if you were working in the plane, this would tell you exactly what is the projection of one vector onto another. And in general, in any vector space, we use this as the definition. So let VW be non-zero vectors in the inner product space. An inner product space is just a vector space with an inner product. V, the projection of V onto W is, let's see, projection of V onto W. This is the definition. It's the inner product of V and W divided by the length of W squared times the vector W. So this is a vector. It's a vector parallel to the vector W because it's some scalar multiple of it. Could be zero, positive or negative. But that's the definition of the projection of one vector onto another.
Professor, can you explain in chapter 5, section 3, exercise 4?
I just pause for a moment. So we have the following, it's an algorithm, which is the Graham-Schmidt orthonormalization method. Given a basis for this finite dimensional inner product space V, compute an orthonormal basis. So I'm going to start with the basis. Let's see. V1 up to Vn. This is a basis So given a basis, V1 up to Vn, I want to compute an orthonormal basis. And let me just note, it suffices to compute an orthogonal basis, because once you have an orthogonal basis, just divide each vector by its length, and you have an orthonormal basis. So, or I can do it all at once. I think I did it all at once in my notes, so maybe that's what I'll follow. But, W1 up to W1. So step one. We have V1, not 0. V2 is not 0. So here's the picture I want you to look at. Here's the vector V1. Here's the vector V2. Now, I can compute the projection of V2 in the direction of V1. The projection of V2 in the direction of V1 is the inner product of V1 and V2 divided by the inner product, the length of V1 squared times V1. That's this. Now, suppose this vector, I take this plus this to get V2. This vector is going to be V2 minus the projection of V2 in the direction of V1. If I add this and this, I get V2. And let me draw a picture to make this a little bit clearer, I hope. Let me just go back to vectors V and W. So here's a vector W. Here's a vector V. This is the projection of V in the direction of W. And that's equal to the inner product of V and W divided by the length of W squared times W. And this is going to be V minus the projection of V in the direction of W, because if I add this plus this, I get V. And I claim that the vector, this vector and W are perpendicular or orthogonal. So I claim that V minus the projection of V in the direction of W is perpendicular, that's what that symbol means, to W. Proof. I just have to compute, well, I'll put the proof over here, the inner product of V minus the projection of V in the direction of W, that inner product with W. That's V times, so what is the projection? The projection is, that's V minus the inner product of V and W over the length of W squared times W, comma W. By the bilinearity of the inner product, this is VW minus this times this. This is a constant, VW over the length of W squared times the inner product of W and W. But the inner product of a vector with itself is the length squared. So these cancel. So I just get VW minus VW, which is 0. So this vector is perpendicular to W. So okay. So I start with the basis V1 up to V sub n. This is a basis for V. Let me make everything a unit vector as soon as I can. So let W1 be V1 divided by the length of V1. So this is now a unit vector in the direction of W, in the direction of V1. It's just V1 times a scalar. Okay. Suppose I let W2 prime be equal to V2 minus the projection of V2 in the direction of W1. So I have this vector W1. I have my other basis vector V2. I look at this vector. So this is the projection, and this is V2 minus the projection. This is the vector I'm calling W2 prime. So W1 and W2 prime are perpendicular. Their inner product is 0. That's what I just showed. If you take a vector, subtract its projection in the direction of another vector, you get something perpendicular to that other vector. So W1 and W2 prime are perpendicular. W2 prime isn't 0 because the vectors in my basis are linearly independent to begin with. So let W2 be W2 prime divided by the length of W2 prime. So what I've done is, first of all, just looking at W1, W2, I get unit vectors. Sorry, starting with V1 and V2, I get unit vectors W1, and so unit vectors W1, W2, linearly independent, and they span the same bases, the same subspaces V1, V2. So there's a kind of inductive step. Suppose I continue this process, and I suppose I obtain unit vectors W1 up to W sub k, k's between 1 and n minus 1, orthonormal, and the subspace spanned by W1 up to WK is exactly the subspace spanned by the original k vectors in my basis. Then V sub k plus 1 is not in this subspace. Let me just call this W sub k. For Vk plus 1 is not in Wk. And I let W prime be equal to Vk plus 1 minus the projection of Vk plus 1 in the direction, of, Vk plus 1 in the direction of W sub I, summation I goes from 1 up to k. So I have various vectors, and I take this new vector V sub k plus 1, and I subtract its projection with respect to all the other vectors, V1, V2, and so forth. So Vk plus 1 minus the projection of that onto all the vectors I previously computed. And I claim that the inner product of W prime with V sub I is 0 for all I from 1 up to k. I'm not going to do that calculation now, but assume that that's true. Now I have a vector W prime, which is perpendicular to the previous k vectors, and I let V sub k plus 1 be W prime divided by the length of W prime. So I've added one more vector to my basis, and step by step, I'm constructing an orthonormal basis that spans the whole vector space V. So, okay. I actually have, sorry, let me just pause. That's really the end of this discussion, and I will work out the example you asked, but I'll do that at the problem session tonight. I'm not able, I don't have the time right now to do it. So let me just pause.